two topics. We'll take a brief break. You want to go to the next slide?
What did it go? Oh, looks like I had to enable. Let me try it again. Yeah, I had to enable editing. Sorry, didn't trust the document.
So then our next meeting is going to be on January 10th, and that's going to be a evening meeting. We don't have a topic at this time. Next. These are upcoming Data Saturdays and SQL Saturdays. These are one-day mini conferences. Some are still offering virtual attendance, so you can give that a try. Next. And this is all about today's presentation. So Dan, take it away with.
All right, let me pull up the PowerPoint here. All right, this first presentation is about indexing strategies. You know, there's a couple aspects to it. One is starting from the, initial development all the way through, reactively doing indexing and, production workloads after you experience problems or want to do some fine tuning. So I'm going to mainly focus on the initial development piece, but, okay. But as with all things SQL Server, the DBA mantra is it depends, and there's no truer case than when it comes to indexing where that applies. There's a lot of trade-offs involved. Indexing incurs overhead in terms of, the maintenance costs and additional storage, but typically, for data, once you've stored it, it's used multiple times. So the beauty about the indexing is that it can be leveraged going forward for many times, because you read data a lot more often than it's been than you modify it typically. Indexes not only improve performance but also concurrency, because lack of indexes, you tend to get a lot more blocking, a lot more deadlocks, and a lot of nasty things happen to your workload. So you still need to consider all these trade-offs in the context of specific queries, and not all queries are created equal. Some are very critical on your workload, and you need to focus on those and tune those as much as you can. And at the same time, you don't want other queries not to finish. You have to have indexes to be able to support those as well, especially as your tables get big and problematic. So the trick is just trying to strike a balance. So there's not a single right or wrong answer. It definitely depends. So this will help at least give you a good starting point, I think, of a strategy to come up with some indexes that'll help you initially as well as help you going forward. So today I'm going to speak to why indexing is important, some of the goals for designing B-tree indexes. Specifically, I'm focusing on OLTP type workload rather than, and also mix, but less so an analytic workload. And the next presentation on column store, I'll speak to more of the analytic aspects of it. But generally speaking, row store indexers are really good for OLTP workloads and hybrid workloads. So I'll review today some of the B-tree index concepts and architecture, as well as the strategy, coming up with a methodology and design considerations for good, B-tree index, and how to, tune queries to help promote, good use of those indexes. So The reason indexing matters is because it reduces costs, both hardware licensing, and if you're in the cloud, the compute costs, Azure, AWS, whatever your, public cloud provider is, and internally it, helps, save costs as well. It keeps your end users happy and productive, since they can get, faster response time and, get a lot more work done faster. What's always realized is that indexing is really the key to really mitigating blocking and deadlocking. So if you have concurrency issues, first thing I like to do is take a look at the indexes, the query plan, whether or not the indexes are being used or not, or if they're missing entirely, that sort of an approach. It'll help, avoid, deadlocks in production. It'll also mitigate the shared resource usage because, efficient query plans that, use indexes properly, you're going to avoid things like, hash matches and, memory intensive and tempdb intensive operations. And, you avoid spills to tempdb and a lot of the expensive, query plan operators. So if you can, have good B-tree indexes, it'll help a lot of things besides just the query performance. It'll help the overall, performance of the, database workload. And keep in the back of your mind that, it's not just about the database. There's also application architecture that, comes into play here. I always like to say the fastest query is the one not done. If you have some, smart data caching, at the application layer to avoid like pulling lists of country codes or, postal codes, that kind of thing. That's, those are, that helps offload, the work into the application layer. So it, doesn't have to use the shared database, back end. Because on the database side, typically you have to scale up rather than out, barring, some, Azure features to do so. But generally for a general OLTP workload, you want to scale up. So the goal of, good B-tree indexes is to keep the logically related data grouped together, in the same, because usually when you have data in a relational database, it's logically related, and hence the name relational database. Now, by doing so, by having indexes that support that strategy, it tends to reduce the number of logical reads, have your, data correlated to the way it's actually accessed and used in queries so that, it doesn't, so the SQL Server doesn't have to do as much work to get the job done. The B-tree indexes provide ordering without actually having to sort the data on the fly to help, optimize the queries. And the high-level goal, the way I look at it for B-tree indexes, is to touch only the data that you need for a given query. It's a little bit easier said than done, but when all is said and done, as long as you're touching only the data that your query needs, your query is optimal. Now, there's 4 ways generally to organize a table. You can have a heap, a B-tree, which just means that you have a clustered index on the table, which I'm really going to focus on particularly here because I'm in the camp that every table should have a clustered index. Now there's some exceptions for specialized cases where you might get better performance with a heap, but generally speaking, SQL Server does a better job optimizing queries when tables have a clustered index. At least that's been my experience. Also, clustered indexes help manage space quite a bit better, as long as you pay attention to normal, regular index maintenance. And by the way, I strongly recommend, Ola Hallengren's maintenance scripts. If you haven't implemented those, they're a godsend. They're a lot easier, at least in my opinion, to use than the, out of the box maintenance plans with, SSIS. You can also organize, a table as a column store or memory optimized. I'm going to cover column store next presentation. Memory optimized, I'm not going to really discuss in any detail, but I'll touch on some of the points as part of the presentation. Memory optimized is really when you need to get to the extreme level of, OLTP type processing especially. It's definitely a nice tool to have, but that's a presentation unto itself, I think. One of the concepts about, B-tree or indexes in general is that they need to have a row locator. Every row in a table has a unique location, if you will, or way to find that row. When you have a heap, it's just the physical location, the file page and the slot within the page that the record exists. I should say where the row exists. Relational database have rows, not records, as one of the SQL gurus often say. With the clustered index, the record locator is actually the clustered index key plus a unifier that SQL tags on at the end of a non-unique key when needed. In the case of a column store, it's the row group ID and row number. In memory optimized table, since everything's in memory, you can use the direct, address of the row in memory as the row locator. So that's extremely efficient. But again, that's kind of beyond the scope here. But the important point for regular B-tree indexes is the row locator is stored in the non-clustered index leaf nodes. So that it can find the row once it finds it by the non-clustered key. And the implication is that, that record ID, if you will, the row ID, the record locator can be used for the row level locking, as well as to find the row, whether or not that row be in memory or on disk. Generally with a heap, you don't have any forward and backward pointers that chain the row together. All you have is essentially a bitmap that represents the pages on disk that have those rows in them for a given table. So to locate a row, if you don't have any non-clustered index, all you have to do is scan the IM pages, which in turn allows the SQL Server to find the individual pages. And that's not a very efficient way to scan a table. And what that also means is that if you have a heap, the row locator is being a physical location on the table. If the physical location of the row changes, it has to also update all those pointers in the non-clustered index. So if you reorganize or rebuild your heap, you have to also rebuild all the non-clustered indexes as well. B-tree, on the other hand, indexes, they provide ordering. With a heap, everything is just in physical order, essentially. There is no logical order. So you don't have any control from a data model perspective or data access perspective, how those rows are, located. They're essentially just stored in insert order. But with B-tree indexes, all B-tree indexes, whether or not they be clustered or non-clustered, are ordered. I've been interviewing some, for a DBA position, and a lot of the candidates, they don't seem to be able to articulate, what a non-clustered index is or the difference between a clustered and non-clustered index. And it's kind of sad in my opinion, but I've had, DBAs say, well, and it's partly true, clustered indexes means that the data is sorted by the clustered index. And that is true. It is ordered by the clustered index. But then I asked about the non-clustered indexes, and a lot of them would say something to the effect of, well, those are random, key values, or, they're not ordered. And that's not the case. B-tree indexes always, regardless of the type, are always ordered. They allow the key values to be ordered in sequence. And that's what really what the benefits of the B-tree indexes are. So the way SQL Server does that is it stores all the rows with the contiguous keys in the same page. In other words, all the adjacent keys, would be in the same, page in memory or on disk. And then the rows within the page are ordered, by a slot array. This is kind of some of the internals, how it works, at the end of the page. And when SQL Server needs to read those rows in order, it goes through the slot array of each page to, return the rows in order. And then the pages within the B-tree index are linked together forward and backwards, referencing the previous and, next page of the chain. So by following that previous and next page order, it can return, the rows in logical order by the key, even if they're not necessarily physically in order inside of the page or on, or in storage or in memory. It can, follow a logical order to return the data sequentially. And a B-tree index essentially is a hierarchy of pages. So this is a little diagram I threw together of how, an index is built, essentially B-tree index. It doesn't matter if it's clustered or non-clustered, the same concepts apply. If you have a brand new empty table, when you insert the first row, SQL Server will allocate the first page for that table, and it'll be empty. The only thing you have is a page header at the beginning and a slot array at the end. So the page header includes the previous next pointer, as I mentioned, which chain the pages in logical order, and the slot array at the end of the the page simply allows the rows within the page to be retrieved in sequence. So when you insert the first row, it's the only row in the table, so it goes in the only page in the table, and in there you get the key columns, you get the unique row locator, essentially to be able to find the row if this is a non-clustered index. You get any included columns if it's a non-clustered index, if you've specified any, and you get all the data columns if it's the clustered index. So the only real difference between a clustered and non-clustered index is whether or not the leaf nodes of the index have the actual data columns in them. So if I insert another key, it puts it in the same page, because all the adjacent keys, by definition with the B-tree index, have to be stored in the same page. And then if I keep inserting data, it just keeps inserting those adjacent keys in the same page until the one and only page in the data for this table fills up. And then once it fills up, does anybody know what happens when the page fills up and it needs to insert a new one, a new row in the B-tree index? Exactly, you end up with a page split. So if I have here, if that one page for that table is filled, and I have to insert a new row, it has to do a split. So it creates a new page, and then it has to take, roughly half of the rows or whatever SQL Server feels like moving, to the new page. Again, these are ordered, so it's inserting, in this case here, the rows with the higher key than the one I'm inserting, half of those into the adjacent page. Logical order, puts the new row in the page that it belongs, with the contiguous keys, and the other ones are higher than the highest key in the page it inserted into. And then because there's more than one page, it has to create another index level. So now we have a hierarchy of pages. The highest level is the root page, and you always have a root page for the index. If there's only a single page in the table, then it's the root, leaf, and intermediate nodes are all the same. But when it does that, it creates two entries or two records inside of the root page, one that one for each leaf page. So now we can locate any given row simply by traversing the hierarchy of pages. So if I look for key number 3, for example, it would try to find the first, or try to find the, by scanning the root page, it'll find that, hey, that key 3 belongs in the first page here, because it's, less than the, key number 5, points to the, the first page in the table. And then it uses the slot array to jump right to the specific key that I'm looking for, like key number 3, as I spoke to. Now, as I keep inserting more and more data in the table, you end up with more and more leaf nodes until the root node, what was the root node, fills up. Then it has to add additional index levels. So the more data or more rows in your table, the more levels you're going to have, and the the larger the table is. You have more leaf nodes, more intermediate nodes, but you always have one root node. So anyway, this hierarchy can be used to either retrieve a specific row in the table by equality, if like by a primary key, for example, fairly efficiently. It has to do, in this example here with 3 levels, it would have to do 3 logical IOs to read any one row in the table. Now, if I read more than one row by a non-unique key, then SQL Server will have to do those initial 3 logical reads to get the first row. But then after that, the adjacent keys are going to be in the same page. So it doesn't have to do any additional logical IO, really. You can just scan through the page that it just read. And if it hasn't got to the end of the scan, like if, let's say if I had only a couple rows, it would all be in the same page, I'd be done. But if there's many pages, like a non-unique key that might have thousands of entries, it'll start using the forward pointers or the backwards pointers, if it needs to do it in reverse, to find all the adjacent keys or the rows with the same value. So, this is the long-standing, B-tree index structure that's very good for equality lookups by unique key. It allows multiple rows to be retrieved by a non-unique key. The leftmost columns, that is. It's very good for ranges too, like date ranges, that sort of thing, to be able to, read the data in an ordered fashion sequentially. By being able to be ordered, it facilitates some query plan operators. I mean, the obvious one is order by. If you have an order by in a query, that's going to need to order data, so we'd be able to use the index for that. But other query plan operators like a merge join or a stream aggregate where it needs ordering to like do a group by clause and that sort of thing, it can benefit from that, the B-tree index as well. So, just keep that in mind, how the B-tree indexes are supporting the, the queries and the, query plan predicates. So I'll jump to a demo here. I should open up Management Studio already, but unfortunately I got a little bit delayed start due to internet connectivity here. I gotta share my screen, I guess. Pull up Management Studio. Give me 1 second while I open up the query. Yes.
The table should get to before it has a clustering index versus just being a heap.
Yeah, the question is, do I have an opinion as to the size of a table before one creates a clustered index instead of a heap? My opinionated answer is 1 row. I do sincerely believe that every table should have a clustered index. Now, again, that's me. DBAs tend to be opinionated, and I'm no exception. It'd only be the table size itself, in my opinion, doesn't really influence whether or not it should be a heap or not. Now, if you have an ETL process, that's kind of an exception where you may want to load into a heap initially, at least as part of a staging process. But once if it's a regular relational database table, I haven't really found a good reason not to have a clustered index on it. At least based on size. All right, so yes, this is a little bit awkward. Oh, there we go. Let me get my. Let me see if I can see the screen a little bit better here. Okay, got it. All right, so so for this demo, I'm just going to create an empty database. And I have a utility proc that I'm going to use in the demo just to dump all the pages of the indexes that I'm creating. So I'll create that proc. So I'll be uploading all the scripts, along with the presentation, after the meeting here. So, that is a pretty, I'm kind of proud of my work here for the stored procedure that dumps these index pages, but it uses a mix of documented and undocumented commands. It does like that DBCC page to, dump the actual contents of the, the B-tree structure. So in this case, I'm starting by creating a table that has nothing more than an identity a primary key, I should say, and just some other data along for the ride. And I made the I deliberately structured this test data to make it easy to eyeball the data inside of the page. So in this case here, I'm inserting 8 rows in the table, exactly like I showed on that PowerPoint a minute ago, where it showed a brand new table essentially with started empty, and then I inserted 8 rows in that table with a varying key value. So this should align directly with the PowerPoint that we just saw. So now if I dump those pages, or dump that page, I should say, because I have a single page in the table, you know, it shows me the page slot information. I'm just querying the, you know, one of the DMVs to get that information. Then I'm also using the DBCC page just to dump the raw contents of the page. So let me show you what that looks like. And like I said, this should look exactly like the, you know, the slide did. Since this is the only page in the table, you know, the previous and next pointers are all 0 because there is no previous or next row. But you can see that, you know, just by eyeballing this here, you know, I inserted row number 1, followed by row number 4, you know, et cetera, 3, and so forth. You know, the order inside of the page really doesn't matter. What does matter for ordering is the slot array at the end. The slot array at the end of the data page actually has pointers, you know, to the, you know, the offset inside of the page where that row belongs. And this is maintained in the proper logical order. So this is pointing to key number 1, you know, the last entry, or first, if you, because it's reading it backwards, followed by key number 2, 3, 4, 5, 6, you know, 7, and 8 respectively. It's just, you know, the offset's 0 based is the only reason it does it that way. It shows it that way. But anyway, that's what it looks like, you know, when you have a single, you know, row in the table. And then if I insert just one more row, you know, which has, this is the one that has key number 2, I believe. Yeah, key 2. And then just, you know, dump it again. Now it's going to have to, you know, split the page, you know, and create the, you know, it has 2 data pages now, the leaf nodes, plus that, you know, index page, which is also the root node. Now these data pages, as I mentioned, you know, you'll see the linkage in here where you have previous and next page pointers, you know, to, you know, be able to traverse either forward or backwards, and the root node where it has those 2 entries in it. And if I look at the actual pages, you know, the raw pages inside of the database, you know, you can see this essentially the same rows we did before in that what was just the first page, and now there's another page. But what I found interesting is that SQL Server, you know, doesn't bother to clean up the data inside of that page after the page split. That first page still has artifacts of the old data that used to be in there, and it just sits out there. So the way I look at it, SQL Server is lazy. It doesn't want to do work it doesn't have to do. So there's no reason to necessarily clean it up. What is important, though, is that it maintains the row offset array at the end of the table, you know, to be able to, you know, locate those rows and return them sequentially. So it basically moved, you know, 5 of those rows or 4 of those rows to the other, you know, page, and then, you know, just didn't bother to clean up after itself. I think all that stuff will, you know, remain, you know, artifacts of, you know, the previous, you know, data until, you know, the Ghost cleanup process needs to run against that page because you deleted some data out of it or something. You know, it'll clean it up then, but for now it doesn't. You know, this is the root node, and it's hard to read, so I'm not going to bother trying to decipher that thing. But then eyeballing the next page, similarly, you see the rows that have moved into the new page, you know, which are 5, 6, 7, and 8, 9. And then the finally at the end, you'll see the row offset array of the last page in the table, in which case we have those, you know, 5 rows. And again, these are the row offset array is maintained in logical sequence. So if I insert a bunch more data here, I'll insert another 100,000 rows or so into the table. This time here, I'm not going to bother with, you know, dumping the raw page and stuff, but I do want to show the just the sequence of the you know, the data. So now it looks like here we have you know, multiple index pages because I need to have you know, a couple of I have 1 root page, 2 intermediate pages, followed by I guess 400 and some odd, you know, data pages, you know, that are all chained together. So, you know, that's essentially how the, you know, clustered index architecture works. Now here, I'll go ahead and create a non-clustered index on that same table. Try to. and just, dump the, just show the logical order of the non-clustered index. Similarly, it has, a bunch of index pages because, the non-clustered index isn't the data page, but it has, 2 levels in this case here. One for the root, and then another for the, or 7 intermediate, level pages, as well for it. And that's enough to be able to locate, all the rows in the table in just 7 pages for the non-clustered index. So non-clustered indexes tend to be a lot smaller and narrower than clustered indexes typically, So any questions about that demo, way the internals work? All right, I'll move on then. Let me pick up where I left off on the PowerPoint. I'm not going to speak to memory optimized, but I do want to call out just a couple things that memory optimized tables don't have a clustered index. They don't need them. It's fast enough just to locate the data directly in memory with the memory pointers. And you can't have included columns because you don't really need them because it's so fast, essentially. There's no faster way to retrieve a row than a memory or a single row by the primary key than a hash table on a in-memory table. I'll kind of leave it at that. So in terms of a methodology for the index strategy, I always recommend that you start with like you probably would anyway, just relational data structures in third normal form or above. Where you don't have any repeating groups, you've identified the candidate keys for your table, and importantly, you choose the most important data or most appropriate data type for each column in the table. Attention to detail is important because that'll help save space and improve performance. Because little things like, for example, if you have a new database that you don't need to have backwards compatibility for, you can use like a date time 2 instead of a date time to save yourself a byte or 2 of space, depending on the precision that you need. And that also performs better in terms of compute cycles because it's easier to maintain it. Or Microsoft back in the day when they, I guess it was 2008 if I remember right, where they introduced the date time 2 type. They put a lot of attention to detail on the structure so they could save space and do it with less CPU utilization. So, consider using the most appropriate data type you can for the given domain of values that a column needs to be able to store, with appropriate data types and lengths. And essentially, it'll kind of inherently save space and give you better performance. Now, it's important from an indexing perspective to always use the same data type consistently throughout your data model. So if you have like a column called, let's say, account number or something, don't store it as an integer in one table and a varchar in another and a car in another one, etc. I mean, try to be consistent so that the data types match, which will help performance of joins to avoid non-sargable arguments. Otherwise, it might have to convert and not be able to use the indexes efficiently. So try to be consistent throughout the data model. So after you have essentially your first cut of your data model, in terms of your indexing, you already get some free indexes with your primary keys and unique constraints. I mean, assuming that you created unique constraints on your alternate keys on your database. Like for example, if you have an employee table with, and I'll say, let's say social or taxpayer ID or something, you're probably going to want to have a unique, constraint on that, for data integrity, if nothing else. And then on top of that, you can create the, additional indexes as needed. So you want indexes to be able to support your where clause predicates. If you got something on where clause, that's a candidate for an index. Your join clause predicates were most often are going to be on your, foreign keys, but not always. But you want to be able to have indexes that support those. And as well as by group by or partition by clauses in your queries and order by clauses. And then, those are candidates that, you should probably, look at creating indexes on. And I'm one that says, or at least suggests that you don't need to create indexes on all foreign key columns, but you probably do. Some people say you always do. Like there's cases where I wouldn't, you know, for example, if I have a table of, let's say, order status, you know, where I have a foreign key relationship between that and the order, you know, table, you know, that'll give me my foreign key, you know, data integrity. But the question is, would it really use that index, or do I have any queries that query on status or status alone? If I always query the orders based on some other attributes besides status alone, that index on status probably wouldn't be, or might not be, you know, selective enough to be of a whole lot of good use. So I wouldn't want to necessarily incur the overhead of maintaining that B-tree index on status, you know, for, you know, every row in the table. And if I have specialized queries that, you know, unless I only need to look for orders that are in, you know, let's say created status after the customer initially creates them, and after they're shipped and I don't care about them anymore, I could actually create a filtered index on status where I would say where the, you know, order status is equal, you know, created. That way I wouldn't have to incur all the storage overhead of maintaining that index for every row in the table. If for, you know, if there's only like a query for a specific value on it. So filtered indexes are a good way to reduce the storage space without having to incur all the extra overhead, you know, and kind of in specialized use case. Yes.
Sorry, just to ask about the first point there. So you're saying create an index on something that will be grouped by partition by or not, because it's already being done in that window function.
Yeah, so the question is, do we need indexes to support windowing functions, essentially? Because, you know, the windowing function itself takes care of that. In order to actually implement the windowing function, there's queries where it, you know, especially, you know, the partition by and the order by, if you have indexes to be able to support those functions, because it has to do ordering, or to do the partitioning, it may do a stream aggregate in the query plan. Of course, queries plans get fairly complex, so there's not going to be a right or wrong answer entirely, but those are candidates for indexes on those columns. So if you have a windowing function where you say, you know, whatever, you know, row number over, you know, or partition by, you know, let's say sales date, and then, you know, order by, you know, something else, then both those candidates would, those columns would be candidates. Now, which of those, it's going to depend on the context of the whole query, because like I said, query plans can get pretty complex, but it's definitely something to consider. And depending on the criticality of the query, as a matter of fact, I have, you know, on second thought, I didn't use a windowing function for the demo coming up here, but I could have. But that would be another possible case for it.
Sorry, I have a kind of similar question. But so does this, so when you're reviewing all these possible candidates, are you suggesting that these be primary, non-clustered keys at a static level, meaning I'm not just doing it for this particular query, creating an index, but it's going to be the index on the table in general for all queries.
So to try to paraphrase the question, should I take a holistic view or not? Yes, you should take a holistic view. You got to look at the whole enchilada, the whole workload, to really come up with the ideal index strategy, whatever that means. There's going to be trade-offs, you know, like if you do, you know, if you had an infinite amount of time, you could spend you know, forever tuning a given query with every permutation of possible indexes or not. So I kind of like to look at the first cut is pretty much like the common sense indexes, and then focus on your critical queries in, you know, in context of those, and then work your way down until, you know, you've spent enough time, whatever that threshold is. Some of the database I work with are quite critical, and I do spend an inordinate amount of time doing performance tuning or testing and index analysis. Whereas others, I mean, you know, they're small, they're not critical, if I didn't have any index on it, it would still work. It's just a question of cost. It already hit heavy enough to the point where it costs the firm, additional money. So, there's not going to be a right or wrong answer, but you want to look at all of your queries, but focus on the most important ones. Yes, sir.
So this tuning is also customer requirements versus the nature of the databases, right? So customers being the quicker performers, does that happen other than others?
So is your question, is the performance need customer driven? In other words, they require.
Is customer also driven? Or?
Yes, your SLAs specifically do help drive, how much effort and how much, what kind of indexing you throw on, a given table. If the CEO is, uses a given application and he insists that his queries be as fast as possible because gets paid big bucks, then yeah, it makes good business sense to, spend that extra time, and that's a driving factor. But of course the CEO would probably also know that he's taking your time away from everybody else while you do that query tuning and all. So not all queries are created equal. Sometimes it's the customer that screams the loudest, frankly. I mean, we all have some of those folks, I think, those databases where, the user seems to always pick up the phone and call you whenever there's an issue and wants all the attention, even if they don't necessarily deserve as much as they're asking. Yeah, but generally you do want to just kind of look at the whole workload, once you're done. So this is really more about the first cut in terms of methodology to, get to a good spot. You want to be, extra attentive to tables that are going to be big. They expect to, get big, because as any seasoned DBA's probably learned, once your table gets really big, then your maintenance window shrinks, and they're difficult to manage. So try to get the big tables right up front, without just ignoring the small ones, because you have your whole workload. Like if your small tables are hit very heavily, you can be the death by 1,000 cuts if they're not optimized for the workload. And when it comes to manageability, consider, table partitioning or view partitioning to help manage those. Really not so much for indexing performance, but it does help things like you can do partition level, index rebuilds and things like that if you have a partition. But partitioning is another entirely, presentation onto itself, because it does have superimposed restrictions on the kind of indexes that you create. For example, if you want to partition your table and it has a primary key that's a single column, you need to be able to add the partitioning column to the primary key in order for it to be the primary key, and that's not always feasible. So you have to evaluate, some of those aspects of, table partitioning. Index views is something to keep in your back pocket, especially for, aggregation queries where, they're expensive and they are executed frequently. I'll have that in the demo coming up here as well. And one side note is to make sure that every time you create a stored procedure, view, function, trigger, that you always specify set ANSI nulls on and set coded identifiers on. Those settings are remembered when you create the object, and they're used at runtime, regardless of the runtime settings of those options. They basically override whatever the session settings are. And the reason that's important is because those are required to be on in order to have filtered indexes, indexes on views, other SQL Server features. So there's really no reason not to have both those options on. But more often than not, I see those leak into production code because, unfortunately, Microsoft chose to implement SQL command, the command line utility a lot of people use for deployments, with set coded identifiers off by default. So whenever you execute SQL command, if you don't have a set option explicitly set in your scripts that you execute, you can inadvertently deploy a stored procedure for with the ANSI, with the quoted identifiers off by mistake. And so you have to specify a -I argument to SQL command to opt in for quoted identifiers. And Microsoft did that just for backward compatibility, but in my opinion, that was a mistake. When they moved from OSQL to SQL command, they should have just said, hey, this is a new utility. If you're going to change the utility you're executing, you might as well understand the implications too. But that's water under the bridge at this point. But anyway, that's a common gotcha, because you don't want to find out that, later that, hey, I need a filtered index and I can't create one because a stupid store procedure was created with your, the settings off. Yes.
You, going back to that, I know partitioning is a totally different thing, but will it, so partitioning helps more with the ETL process of it, when I'm loading the table, how it does, how faster it does. I don't know if it necessarily helps with the reads. Would it be helpful to have, and most of the times the way we partition is using like a datetime field, with just our date field, so the card not being slow. Would it make sense to have the same field as a partition and also the clustered, non-clustered view, so the non-clustered index, sorry. So for the ETL process, it's faster using partition. Also for the actual query, it's faster using the index.
So the question is it appropriate to have a partition table to support a ETL process essentially, and also have a non-clustered index on the partitioning column to support other queries? They're really independent choices to at least to a degree. I have an entirely separate partitioning presentation that I've done here before a couple of times, and it's kind of getting old. That's why I didn't want to do it again soon. But it's like you mentioned, it's common to partition, using a date time by month, by year, whatever that makes sense. And one of the sweet spots for partitioning is not just for manageability, as I mentioned, but also for ETL, where you can do switching at the partition level in and out of the table. So you can load, let's say, a full days of data and switch it in instantaneously, or switch it out to purge or archive, that kind of stuff. In order to do all that, your indexes have to be aligned. And the question is really then, what is the best choice for your clustered index? I don't know. It depends on your queries at the end of the day. Most of the time, when I do date-time partitioning, I tend to also have the date-time column as part of the clustered index key. Usually, they're very focused on date ranges. Not always, mind you, but a lot of times. The biggest table I've ever had to work with myself, that was partitioned, was about 60 billion rows or so. And it was partitioned using the only cluster index key was date time, because it was incrementally loaded with bulk insert, and there were all other considerations as well. But that helped eliminate a lot of the fragmentation while loading the table all the time. It was continuously loaded throughout the day, not just as a part of the ETL process, but then had multiple non-clustered indexes that were also partitioned and aligned, that were focused for the queries that they normally ran against that. But most of the queries, importantly, were focused on narrow date ranges. Seldom did they really have to query months, across date at a time. So it's going to definitely be one of those it depends things, and there's going to be whatever I say, I'm going to be wrong, because there's going to be some outlier where that's not the case. But so again, it's
for a normal average case scenario, that would be fine. We're not worried too much about outliers, just normal case scenario.
Yeah, because your clustered your partitioning column is going to be implicitly part of. It's going to be if it's non-unique, it's still going to be part of the clustered index key. Like it or not. So it's going to factor into that anyway. But if you also need, but if you don't want it to be the high order leftmost column of that clustered index, and you need to be able to query on date, then you need to have a non-clustered index, with that date time as well.
Thank you.
All right, and to that end, kind of segue, the order of the keys is important when it comes to your B-tree index definition. As a general rule of thumb, we want to specify the quality predicates first, so that if you say, where column A is equal to B or to some value and column B is equal to some value, you want those before you have other columns. So if you had, let's say, a 3-column index of, let's make one up, order ID and order date, then you would want to have the order ID first, followed by the order date. And then all things, after you've done that, then in other words, that would be assuming that you select ordering on where the, let's say, order ID, that was a bad example. I'm trying to think of a better one here off the top of my head. You want to have the sorry, I'm trying to think of better here. Let's say for your I'm just drawing a blank right now, not thinking on my feet, my apologies. But you want to make sure that, the clauses that are specified equal, or, that those are the leftmost columns with the index. And then things that are inequality predicates, such as the a date, where you're doing date ranges, or, after the equality predicates in there, where, I want to see where the, customers that are, between certain dates or something like that. And you want to have the most selective keys first, generally speaking. But the real important exceptions, though, come when you think about your data model. Oftentimes, you model your data such that the, especially when you have, parent-child relationships, where your child table isn't like a standalone, identity column. At least it might be, but in a lot of times, the way it should be modeled, at least, is where it includes the parent table primary key. So it'd be a composite key of, parent table, plus some other attribute in the child table that distinctly identifies the, the row in the table. So the composite key is really your primary key on the child table. And when you do that, you tend to also, of course, join on that column. So that it kind of does double duty then. You end up with a table that, or an index, your primary key index, mind you, that satisfies that join criteria, because one often joins from a parent to a child table. So that's why, it's always a good idea to specify those columns first, even though they might not necessarily be the most selective columns. They are used in, the equality join predicates. Let's see, I had a hard time articulating that last bullet here to a single index that could be used by different queries. So in the context of a composite index, where let's say you have 3 columns, what I'm trying to say there is that, if you have a query that just selects on column A, where column A is equal to some value, and you have another query where column A and column B is equal to some value, you would want to structure that index such as the column A would be first. That way, that one index could be beneficial or equally beneficial to both those queries. And it doesn't matter how many columns you have in it, the same rules apply. So just be aware of that when you have multiple, when you have composite indexes. And I already spoke to my, I kind of alluded to it. Pet peeve of mine is when I see a data model where every single table has a column called ID, named ID, and it's an identity column. That's somehow, I think, like, some DBAs think that makes your data adhere to normalize, because every table has a primary key. I'm all for primary keys, but don't make it mindless, especially on the parent-child relationships, and then association tables, where you might even have 3 associations to that, table. There's multiple, your data models can get quite complex at times, but a lot of times the primary key should be a composite key, that's been migrated, from the parent tables, what they call an identifying relationship in the data modeling world. And that way you get both data integrity and performance when you start joining on that. Sometimes though, because the key order matters, if you have a association table where you have, you have table A and table B that are your parent tables, and then the association table in the middle that are joined, you can't have your cake and eat it too. You're going to have 2 indexes really to be able to support the joins from the different directions sometimes. So, just be aware of that as well. Yeah, Julie.
So I've been of the mindset with you that every table should have a cluster index. And I've asked on some, and they're like, all the columns are needed to be unique. So what is your view on having a clustered index with all the columns versus going ahead and creating that identity? They'll never reference or go in by the identity.
So I'm not sure I fully understood the question in the sense that all the columns are unique. What do you mean by that exactly?
No, I mean, they need, when I ask them, well, what do you need to be unique? I said, let's say the table has 5 columns, well, we need all 5 columns to know our uniqueness. So it's that, or they're saying, well, I can create an identity, but they'll never go in by the identity, or a non-clustering index on the columns that they're frequently.
All right, so as I understood it, an example is you have a table with 5 columns, and the natural key, and I'll put that in little air quotes, are all 5 columns of that table. Is there any value in introducing a surrogate key, like an identity column on that table, just to call that the primary key, especially when you need to have another index anyway to support the other queries, because you don't have any queries that would query.
Should you have the clustering in, or should you create the clustering index on all 5 columns?
Right. So yeah, so really I would say double duty, and that's create the primary key with all 5 columns and make that primary key the clustered index. The primary key does not have to be clustered, nor does the clustered index have to be the primary key. So it's going to depend on your queries what the best strategy is. So if you did have, in the example that you just gave, where you had 5, that may be fair. Let's say these are wide columns, and the downside to making that the clustered index is that if there's any tables, if that's a parent table, and there's a child table where you have 6 columns is the primary key really. Is there value in, or the downside there is the extra space that you would need to have for because all of your non-clustered indexes will have all 5 of those columns replicated as part of the row locator. So that is a downside to having the wide keys. But on the other hand, and the positive is that it does tend to cover queries a lot. And if space is an issue, you can throw data compression, either page or row on the thing too, and then it'll help mitigate it. Maybe let's say I'll throw out a number and say 20%, 30% in terms of the space utilization. But it's going to be the case by case basis again. One of those it depends things. But the one thing I would never do is throw on a surrogate key to call it the primary key and never use it. Now, if you use it, that's a different animal. One of my pet peeves is a log table, which isn't a relational table, but everybody has them. You have some table where you keep some history or throw application log messages into or something. There's no reason to create an identity on that column, on that table. If you're be better served most likely just making a clustered index on the insert timestamp or something, and then that way you get the benefits of the incremental loading of the table or inserts, so you don't end up with many page splits and stuff. Yet you still, don't have an extra index that you never use. So it's going to be one of those it depends things. I mean, it's okay to use SQL Server as a storage engine instead of a relational database, but its sweet spot is really relational databases.
So you're recommending that all tables have clustering indexes, not best serves the use for the.
Correct. I would recommend that. I mean, non-unique clustered indexes are okay. And just in general, unique indexes are preferred over non-unique indexes. But obviously, you know, if you have a situation where the key is not unique, it's not going to be unique, you know. But that does bring a point. I think I call it up in one of the upcoming slides here, is that the non-clustered index. I'm sorry. It's a common oversight to create a index, you know, especially a non-clustered one, without declaring it unique, even though the values are unique. It doesn't really help, you know, it doesn't improve the index, you know, quality much, you know, by declaring it unique, but it does help the optimizer, because the optimizer, knowing the values are unique and will always be unique, it can optimize the query and do things like avoid a nested loop operator, depending on the details of the query plan and things like that. So the story is that, you know, if your index value keys are unique, declare them as such. It's part of the index grade. One thing that a lot of folks aren't aware of is that, you know, or you may be aware that, you know, you can't have included columns when you create a primary key constraint or a unique constraint, at least not at the current time. But you may not be aware of that, you know, a foreign key does not have to reference the primary key. A foreign key can reference a unique constraint or any unique index for that matter. The only difference really is that a primary key constraint will always enforce the fact that your underlying columns cannot be null, whereas a unique constraint or a unique index, you know, the DDL isn't going to require that be a not null column. So if you have situations where you really would like to have a non-clustered index, you know, on your primary key with some included columns, you can do that, except you just can't do it with a primary key constraint. You actually have to use a, you know, just a create index, you know, syntax to create a non-unique index, or I'm sorry, a unique index, so that you can also include, you know, included columns. So that's something to keep in your back pocket, you know, that I think can be helpful in some cases as well. All right. Let's see, time check. It's been around an hour here. Yeah, sorry, I got started a few minutes late here. Let me move on to my next demo. Escape out of here and go back to Management Studio. Let's see. Okay, so for this, I'm just going to use the out-of-the-box AdventureWorks 2019 database, which you guys may be familiar with. It's just a sample database that Microsoft gives us. And I just want to show the indexes that, you know, the person that designed this data model came up with. So I listed all the tables and all the indexes, and whether or not, you know, the indexes are clustered or not, and whether or not they support a constraint. And whether or not they're unique. Essentially, this is just a summary of all the indexes that exist in the AdventureWorks database. Now, with this one here, I mean, it's not a bad data model, but I wouldn't call AdventureWorks the poster child for, you know, data modeling either. But it does have some interesting aspects, and the one I want to call out to the point we were speaking of a minute ago was, you know, about the, you know, use of, you know, identities and you know, throwing those on a table. Looking at the sales, and this is database, or I'm going to use this one in the demo anyway, so might as well speak to it here. The sales order header table, you know, it has a primary key, that a clustered primary key at that consists of, you know, I'm sorry, I said the wrong one. I meant the sales order detail table. Oh, I was past it. Yeah, alphabetical order. So the primary key of the sales order detail table, which is related to the sales order header, is a composite based on the sales order ID, which is the migrated, primary key of the, sales order header table, and the sales order detail ID, which is a identity column. So in this case here, they didn't just put a standalone identity column on the table. They deliberately made a composite key of the sales order detail, as they should, because this is really what they're going to be joining on, is sales order ID. And then, just incremental value on the sales order detail ID. If there was a natural key on this table, like the sales order detail, for example, if you could only order a product once on a given order, probably instead of an identity column, they should have chosen, like the product ID or something like that. But I guess for their business rule, maybe they could have the same product multiple times on an order, maybe different quantities or something. I don't know. It just depends on the business rules. But, this is as good a way as any to do it, I guess, especially if even though none of the orders in the database, I ran a query just to ensure, but none of them have more than one product on a single order, the same product, I mean to say, on this order. So I did create a little database diagram. Resolution here is a little bigger than I thought it was going to be. Hopefully that's somewhat readable. But anyway, we have the tables that I'm going to do this demo on. We have the customer table, we have sales order header, which is the orders for the customer. And then we have a customer order detail, which has all the items that customer, ordered on that order. So what I'd like to do then is go ahead and, just show you some queries in the way, you can apply that indexing strategy to, improve performance. So this is just a hypothetical scenario. So let's say, this is a e-commerce company. They have a presence on the internet and they have a lot of customers. And whenever a customer signs onto their website to place an order, the customer gets a list of the orders that they currently have, outstanding. And on that web page, there's a paginated, little section on the page where, they get a list of their, recent orders. So to do that, run this query to, return and the application specifies how many rows per page and all that stuff. So if the customer has more than, let's say, 10 orders, that they can, page, through the orders, but they always see the most recent ones, top, So I created this stored procedure in the AdventureWorks database, just to get an idea for, just a theoretical thing, how what a common use case you might be to query orders. And let me take a look at the execution plan here. So here I included the actual execution plan. So this is just, like I said, pagination. So I just give the proc just takes the customer ID and then the page number and the page size. So it just displays the most recent orders for that customer, on the client facing, page when the customer logs in. This is the first thing they see. Let's see here. Oops, I forgot to restore the database. Hold on. I didn't clean up after my last rehearsal here. Let's see. Thought I had this set up here. Where's it? There we go. All right. So I just restored it. So now the database is back to the original place it should have been. So I'm gonna have to recreate my stored procedure here. All right. So the execution plan for that query, I mean, it's honestly, it's not too bad. We see index seeks here. So it basically does a seek to, find all the orders for the customer. And then it needs some additional data. So it has to do a key lookup on the sales order header table to retrieve, I can see in the output list here, the order date, ship date, and status. So it gets all the orders, and then it, for that customer, but it has to sort them. So depending on how many orders that customer has ever placed in history, it has to sort all of those. And then of those, it takes the, essentially the top 10, which is how the, the pagination is actually implemented under the covers. So, is there room for improvement? I think so, but just to quantify it here, I tried this on a bigger screen resolution monitor, so this is going to be kind of tricky here. But there's the performance counters. So I'm just monitoring CPU utilization, number of batch requests per second, and all that. And then let me go ahead and see. I think this will do it. Yeah. So I'm running a utility that comes with the RML utilities called OSQL Stress, I guess is what the name of it is. What it does is it OStress, I should say. So what this is going to do is just going to execute that stored procedure as fast as it can. In this case here, I have it configured for 100 threads. So this is like having 100 different, web servers, if you will, with users hitting, logging on as fast as they can. So if I look at the, the metrics, the CPU time right now is pegged, as you might guess, because, there's no throttling or anything with that workload. The page lookups per second, it's almost just under 1 million. Per second, and it's doing it at a rate of roughly a little over 20 some odd thousand requests per second, which isn't bad for a laptop in terms of the database. But right now it does fluctuate as things get warmed up here. But yeah, so right now it's going to be about 30,000, looks like. But in terms of improvement, what I'd like to do in this query plan is get rid of that sort operator. So rather than to do that, let's see, yeah. So what I did is I just added this is using the index on just customer ID right now. So I added the order date as another column to that index, and I'm also using the online on drop existing on. And that drop existing allows you to use a create index syntax to essentially modify an existing index without having to resort all the data from scratch. So because I'm anal, I also rename the index in the process here. So if I execute that query, while this thing's running, and then go back to the CPU utilization, let's see. Yeah. So the processor time, where it was nearly pegged, now it's down to about 30 some odd % on average. The page lookups still, I guess, is pretty darn high, but the batch requests per second improved. So instead of having roughly 30,000 per second, now we're up approaching 40,000 requests per second. And if I take a look at the new execution plan here. No sort operator.
Are you able to show that in the share?
Oh, I'm sorry. I did not realize I wasn't sharing the performance counters. Well, fortunately, I have it set for a high resolution here. This might make a little more sense. I hate when I'm talking about things that you can't see. So that black line right now is the batch request per second. But importantly here, the CPU utilization is the, overall. So when I first started the test, before I made that index change, CPU was pegged, and you can see how it dropped dramatically when I created that, when I added that additional column to the index and avoided and eliminated that sort. And then the batch requests per second, the throughput, to measure how much work it's doing, that increased. So I'm doing more work with a third, about 2/3 less CPU time. So that's what you want to see, is less resource utilization and greater throughput, just with that one index change. And all that was is, and by adding that extra column to the index, it got rid of that sort operator. So again, indexes can be used to help, your order by clause, which it needed for the pagination. Now there's still, though, we see that key lookup. So I'm going to get rid of that guy here just by adding an included those two columns that are missing from that, or that it's doing the key lookup to get. If I hover over here, I can see it's, grabbing ship date and the order status. So if I add those to that same index, also using that drop existing syntax, now, did that thing finish already? Oh, there we go. All right, it just wrapped around just when I did that. Yeah, so now we see the batch request per second, it upped it a bit. Before it was running maybe just under 40. Now it's running just above 40. But in terms of the CPU time, the CPU time is way down now. It's down averaging, let's see, just about 6%, 8%, 5%. So it's it's well under 10% CPU time. So that now the database server has a lot more headroom, just by adding those included columns, avoiding that nested lookups. And, let's say that was Black Friday and everybody's happy. And now guess what? Cyber Monday's coming along, and the sales guys decided to run some, commercial to hawk the website stuff. So if that's not good enough, which this is good enough in my opinion, 99% of the time, but if it weren't, we can also, or let's say, let me add a little spin on here. Let's say that we have a requirement to not just return, the recent orders, but also the number of items on each of those orders. So we'll, see what happens here. So what I did here is the same as before. I just added a subquery to get a count from the sales order detail table. And because I don't really have an optimized index to be able to support all of that, the processor time jumped up considerably and the throughput dropped, as you might expect too. So, just to pull out all the stops, what I'll do is just create an index view just on the, the sales order detail table that materializes the order count by sales order ID. So if I run that guy, now I have an index view that has the count of the orders that supports that subquery. And let's see, it should. Okay. Oh yeah, I also have to create the index on it. I created the view, I forgot to create the index. And now that I have the index on there, the CPU utilization will drop, and go back, and it'll go back up again, or the throughput will jump back up as it should, because that now it doesn't have to go through all that work to get a count of every all the orders for each item. It's basically back to throughput isn't quite as good as it was before I had the subquery, of course. I'm doing a lot more work, but it's still a lot better than it was, and it satisfies the business requirement of being able to see the count of the orders. And CPU time is went up a bit too, because some of these customers do have quite a few orders. And just to look at the execution plan on this, whoops, hit the wrong button. Okay, and just to look at the execution plan on this one, the so it's doing a index seek just like it before, and now to get the count, it's just doing a clustered index seek on the view. So, Enterprise Edition and, Azure SQL Database, once you get up to the higher tiers, will be able to use the index view even without that view being referenced in the query. For lesser editions, and a lot of times, even with Enterprise sometimes, you have to add a no expand hint, to the query in order for it to use the index view and use the view directly in the query. I didn't have to do it here because I got lucky, I think. By the way, I'm using SQL Server 2022 for the demo here, and running native compatibility level. So I don't know if that has anything to do with it too. And just to show, I'll just go ahead and just turn on compression on some of these tables. Row, row and page. Just to show you real quick. Oh, did I? I'm sorry. What?
I thought you were going to get an error because the initial run that you had not selected.
Oh, okay. Yeah, I lucked out and there I did. You're right. Oh, I didn't select the comment. Yeah.
A single.
Well, I don't aim very well with my mouse sometimes. But anyway, this isn't really core to the presentation, but I wanted to show that, by turning on compression, it did reduce space, somewhat, not a dramatic amount, before and after. Well, this one isn't too bad, for the sales order editor, by maybe about 30% or so. But the main point I wanted to make is that it did not affect the CPU utilization at all for this workload here, which kind of surprised me, to tell you the truth. At least it wasn't measurable for hammering it like this. So if you're either memory constrained, where you can't increase the memory on your server, or if you're storage constrained, where you need to reduce the size of your database, I would definitely suggest you do some testing with page compression. It's a pretty simple implementation. All I do is just do a create index with drop existing with the desired compression level, and it helps out a lot. Anyway, run a little bit over for the presentation, which is, I don't know, could be a good thing or a bad thing, but just want to make sure I got most of that stuff in. Any other questions here? Yeah, I'm going to blow through the remainder of the slides fairly quickly, just to be complete. I spoke ahead about, to some of these index options and stuff, and I would like to, discuss those a bit. Let's see, let me get out of my demo. Let's kill this thing. All right, I'll just cover some of the index options. I already pretty much demoed most of these here. Just to review, you have your options on your B tree index, cluster, non-clustered. I think, we all know what that is. Unique or not, include, to get additional columns in your leaf nodes. Where for filter, ascending or descending, and also the data compression that I just showed there. And, I won't detail these because I think you already know what all that stuff is. There is another index option I didn't speak to, but there is this optimized for sequential key, which can help performance to reduce page IO latch contention at very high insert rates if you have many concurrent threads inserting to the table. I just want to mention mainly that I haven't had a workload that needs to have this option set yet, but one of the things that they do caution about in this blog post that I referenced here, from Microsoft, is that, you don't want to use this option indiscriminately. You really only want to use it if you actually see page, latch contention due to incremental inserts, hotspot at the end of the page, where you would typically need to have a lot of concurrent threads inserted into the table. So essentially what it does, it just throttles throughput just to reduce the latch contention, which can help overall throughput, but you still end up with a little bit more latency and actually slow down the inserts of individual inserts a little bit. So I just wanted to call that out. Incremental keys are good, at least in my opinion. It helps. It manages space better in terms of your B tree index by reducing fragmentation. Importantly, though, it'll also improve your temporal locality, basically meaning that the most recent data is most likely to remain in memory, and there's usually relationships between your date time and your incremental values. Like if you had an insert timestamp and an identity column on a given table, and then selected from that table, you would see the strong correlation, obviously, because every time you insert, you get a higher identity as well as the later timestamp. But by being incremental like that, even though there's not necessarily a logical relationship between that recently inserted data, it does tend to group those together physically closer, such that they tend to be in memory, because people tend to get their most recent orders and that kind of stuff. So there's a number of options you can use to generate incremental keys, surrogate keys. You can use identity, sequence, new sequential GUID, get date, not necessarily key, but that's incremental value. But I want to call out that you can also do it in the application code. The newer versions of Entity Framework introduced this sequential GUID value generator class, which will generate a sequential GUID that can be assigned in the application side. And I've had a good success working recently with an application where they needed to insert, hundreds of rows at a time into the database. So instead of doing individual round trips and and having the database assign the values and then return those back, back to the application, because the application needed to know those values to call a downstream service. The application actually uses that value to generate its own GUIDs in a sequential way that SQL Server doesn't fragment things. So with that sequential GUID generator, the rows will end up in the same pages in the B tree roughly, and it'll help provide an incremental key, without causing a lot of fragmentation and stuff. But both the new sequential GUID and sequential GUID value generator, just be aware that those values will be incremental only for the lifetime of the thread, if you will. So every time you restart SQL Server, it'll start a new sequential GUID sequence. Every time you restart the application code or service or whatever it is, you'll get a new beginning sequence of that sequence number, because it's based on all sorts of magic under the covers. So it won't be universally sequential over time, because every restart starts a new one, but they will tend to still be incremental, and there'll be, there will be some temporal, locality associated with it too. At very high insert rates, and I mean the extreme level, you can run into some of the latch contention as a downside with incremental values. And that's where you would need to maybe worry about that, optimize for sequential key option. Random keys do inherently avoid page IO latch contention, because every row essentially ends up in a separate page, but unfortunately that also just absolutely kills your buffer efficiency and buffer cache. Especially when it's on the clustered index on big tables. So I would recommend that you avoid those for surrogate keys, unless you have a absolute special reason not to. And if your app devs use GUIDs, to generate their own keys, make sure they're aware of that sequential GUID thing. I'm not going to talk much about fragmentation, going to run a little late anyway. So in query tuning, just be aware that SQL is declarative, not procedural. I'm sure you already kind of know that. So ideally, it'll always give you the best execution plan and leverage whatever indexes you have, regardless of how you express that query. In other words, where exists should be functionally the same as where in, things like that. But it doesn't always work out that way in real life. So you still have to look at your plans. But importantly, when, as I mentioned, make sure your data types match. So that'll help make the expressions targetable. So any stored procedure parameters or function parameters, whatever, make sure that they match that of the underlying column, and avoid applying functions to the where clauses, because that will also prevent the index from being used. So you want to make sure your expressions are targetable. So always look at your plan to make sure that the indexes are being used as expected. And just this is a common example I often see, is where you want to see all the orders for a given year. So you say where year order date is equal to year. I mean, that's a natural way to express it. And at least as the last time I checked, SQL Server wasn't smart enough to optimize that. I don't know what it really could do, because it has to extract the year from the value before it knows what the value is. So what you can do, though, is refactor the expression such that the column stands alone on one side of the expression. You have your column, and then you have your criteria on the other side. So that functionally, this gives you the same functionality as a year. And this could be you could put get dates and some date math on the right hand side too. But that's targetability is important. One big gotcha that I've seen on applications is that they accidentally use Unicode parameters for strings. It's very common in Java and .NET because strings are generally Unicode. So if they pass the value, it'll without strongly typing the parameter, it will pass the value as Unicode. The big gotcha is that if you have a SQL collation, a legacy SQL collation, like is the default collation in the United States. If you happen to be Great Britain, it's a Windows collation. Don't ask me why. I mean, I do know why. It's backwards compatibility, because mixed collations, you'll shoot yourself in the foot. But anyway, most of us use SQL collations. If that's the case, be very attentive to the fact that don't pass Unicode parameters to compare a varchar column, because then it will be non-sargable. You end up doing a scan and it won't be able to use the index. So if account number is car or varchar here, it won't use the index if you have a SQL collation. Windows collation it will. And there's also a programming technique that is very common to use in .NET to add a parameter. It's called add with value, in which case you just give it the parameter name and the value. Well, the problem there is that in .NET, strings are Unicode, so it implicitly defines that as a Unicode parameter, so you end up not using the index. I've seen a number of deadlocks and that kind of stuff get resolved just by the application change to pass a varchar instead of an nvarchar parameter. That's just another example of non-sargable. So anyway, summary. The goal of the indexing strategies is to make sure that only the data the queries needed get touched. You want to proactively examine your execution plans, tune the queries so that the indexes can be used efficiently. And I didn't have any demos, unfortunately. But anyway, there's a number of DMVs that will identify index use, so you can back into the fact that they're whether, when, and how the indexes are being used. Some of those are ephemeral, so that they get reset every time SQL Server restarts. So you need to keep that in mind when you do that. So just because you don't see index being used today, it might be used tomorrow, but if it's not used every day, then maybe it's not all that useful anyway. I don't know. It just depends on your queries and the criticality of them. So anyway, that's the presentation in a nutshell. Went a bit over, but the next presentation I think it's going to be a bit shorter anyway, so we'll still end up on time. I think we're ready for a break.
We'll just be taking a brief break and then we'll start up again.